the next session. So the first speaker is Professor Kang Yang from Institute of Strategy of the Chinese Academy of Sciences. Title is Hidden Analytic Structure of the Heat Transmission.
Thanks for the introduction and thank you. Thanks for the organizer for the opportunity to speak here. So today I'm going to talk about this two-loop Higgs amplitudes, and it's based on the two papers appeared this year and in progress, which is mainly in collaboration with Jin Jin, who is postdocs, and actually is going to take a faculty position in Chinese Academy of Engineering Physics. Also with another postdoc, Korean, there's some work in progress. So for some of you who attended this meeting last year, so I talked about the direct connection between polynomials and QCD, which is meaning for the maximum Shannon part of Higgs to 3 gluon scattering amplitudes is identical to the 3 gluon form factors in the polynomial theory. So after that, the question we want to ask is how about Higgs amplitudes with fundamental quarks? So this is really the SU3 quark states that Higgs to, for example, to the quark pair to a gluon. So the color structure is very different compared to pure gluons. In this case, you may say, okay, they are both adjoining particles, the connection is nature, and they also actually only a natural contribution. But this, for quarks, we have non-planar corrections. And we found actually, even in this case, the hidden relation still exists. And also we try to understand deeper what's the reason behind it. So in this talk, I hope to give you some updates. So this is the motivation outline of the talk. So first as the motivations, this is a general strategy for the loop computation in QFT. So normally we start with Feynman diagrams, right? We write down the expression of the Feynman integral. You can also use the on-shell intelligent methods to obtain this integral. This would contain thousands of terms, even in very complicated cases would be millions of terms. Definitely we cannot do them one by one. So the next step is to apply some integral reductions. This typically that you have a much smaller set of master integrals, so your very complicated expression can be written in a very small set of integrals times the coefficients. So for these integrals, you can do evaluate the integral, find the analytic expression, then time these coefficients to get the functional form, right? And if you just naively do this, then it still can be very complicated. However, in many cases, people find there is a functional identities. So surprisingly, in many cases, what the final result, these functions, is much simpler. So at this stage, normally you encounter huge intermediate expressions. So to give you concrete examples, this is the famous Taylor formula for arbitrary n gluon amplitudes, which you have a 2 negative helicity plus or plus helicity. So the final result is just a single line expression. And in contrast, if you look at Feynman diagrams as an n number of gluons grows, the number of graphs grow factorial n. Just look at the very simple 5 gluon expression, it will be already very non-trivial. So the lesson is that this structure is hard to understand if you're using Feynman diagrams. As another non-trivial example is the 2-loop 6-loop amplitudes. So there is a hierarchical computation. Basically, the by Feynman diagrams do the computation to get a 17-page of expressions, and each term is a 4-dimensional function, so-called multiple polylogarithms, or Gamchico polylogarithm function. So remarkably, actually in the same year, the group of the Brown people, Brown University, they managed to simplify the 17-page in terms of basically a line of very simple classical polynomial functions. So the main lesson is that such simplicity is totally unexpected if you look at Feynman diagrams. So there's also other examples. So this is a very strong hint why people are interested in taking a new modern view to study amplitudes. And so conceptually, you can say there should be new structures or new formulations of QCD. And indeed, there are many toy models have been understood that, for example, William-Twister theories, Grossmanian, CHI formalism, or some new geometric structure, etc. And methodologically, it is also people have developed very powerful new computational techniques. For example, spin analysis formalism, BCFW recalculation, unitary CAS, and new integral reduction and integration methods. So just to emphasize, for example, this BCFW recursion tree-level methods and unitary CAS, they are now really used in LHC. For example, the one-loop computation and at high loop. But if you look at the original paper, they are really studying the X4 polynomials. So by studying very toy models, this you can really learn a lot, which can have impact to realistic physics. So I think many of you should be very familiar with such polynomials. So I just gave a very brief review. So it's a QCD maximally supersymmetric cousin. It has the same Bloom field, but also with the superpartners, which are fermion and scalars. And they are all in the joint representations of this gauge group. So it has very special properties. So the question that we want to ask is what can we learn more from source polynomials for realistic QCD? So probably there's very few known relations. That one of them is the so-called maximum transcendentality principle, which means that the source polynomials, if you look at the maximum transcendental parts, it's equal, really equal between the QCD. So just by knowing source polynomials, you know a very non-trivial piece of the QCD results. So normally in this side, you can do to very high loop order and sometimes even non-positive. So hopefully this can tell us more about the QCD. Of course, this is still conjecture. So just to tell you what's the meaning of this principle, so that this is related to the mathematical concept of transcendentality. So let's look at how about the transcendental number. Okay. The definition is that whether it can be taken as a root of a non-zero polynomial equation with integer coefficients. For example, this is a very simple equation. So square root 2 is a solution of this equation. So it is an algebraic number. And if the answer is no, then this would be defined as a transcendental number. For example, the E and pi, they are transcendental numbers. And similarly, this the definition can be generalized to functions, which has non-trivial dependence on variables. So whether it's an analytical function satisfy certain polynomial equations, which is in contrast to algebraic functions, for example, the rational functions. So the transcendentality actually can be also classified according to their complexity, which is given by this degree, transcendentality degree. Okay. So if you look at algebraic number or function, they have degree 0, which is just to say, okay, it's not transcendental function or number. And if you look at pi or log, it has transcendental degree 1. Okay. And if you multiply function together, their degree added up. Okay. So if pi square, it's degree 2. If it's log to the third power, it's degree 3. Okay. And there's more non-trivial function like multi-zeta value or the polylogarithms. Okay. So you can see by definition, this degree k is basically, for this polylogarism, how many dimensions of integrations. So it's the higher the k, the more complicated this function would be. Right? And because we will use dimension regularization, so there will be this minus 2 epsilon this component, this regulator, this epsilon will be defined as a degree -1. Okay, so it's maybe exactly is understandable because the higher degree, right, the simpler the function would be. Okay, so this is like a balance between our functions. Okay. So if you have higher degree, that would be much less active, then it would be times a more complete function. So this would be -n plus n, which will be cancel with each other. So that's, I will maybe later show some examples which is contain this extension. But this is just a definition. So this the correspondence was first observed by the Liptov and collaborators. They studied this anomalous dimension with two operators, and it is found exactly that is N4. This anomalous dimension is identical to the maximum channel parts of QCD results. So of course, the anomalous dimension is still a number. So, and later we found that for Higgs to 3 gluon amplitudes, but with this the top mass to the infinite massive limit, that there's this correspondence still preserved in this case. So this is a QCD computation. And it turns out that this is a result is precisely identical to the N4 superior result, which actually is given in a much simpler form. So these are still backgrounds. The question we want to address in this talk is to which extent is this correspondence correct? Okay. Because it's, as I said, it's still conjecture. And what's the origin of this correspondence? Why this has to be true, okay? And to which extent it is true? And also, can we go beyond the N4, right? So far we talked about the maximum channel parts, right? How about the lower channel parts? To get the full QCD results, if you really want to make this correspondence into practice to be helpful, you have to find a way. How about the lower channel parts? Hopefully, we will address all of these questions in this talk. So let me make more explicitly what's observable we want to consider. So the physical process is really related to the Higgs production in the LHC. We have the two hadrons. Then the dominant production channel actually for Higgs is a so-called gluon fusion. But Higgs has no direct interaction to gluons, so it is through a Yukawa coupling to a quantum pair. Okay. And the coupling is proportional to the mass of the top, so it's dominated by the top mass, top, which is heaviest top. So you see the leading order would be the one loop computation. Okay. The people find actually a nice trick, which actually a very good approximation is to integrate out this top, take this MT to be infinite limit. So what we have is an effective theory, which has direct coupling Higgs to this trace F squared between two gluons. So this is just an approximation, and this is effective theory, not understood as a standard model effect theory. It's just for this simplify this computation. So this has been carried out to the next to third leading order for the Higgs production, which is it's an important input for the Higgs experiment. And if you want to, it turns out that actually, if you want to look at the new physics, or it turns out this Higgs plus 1 jet production is actually sensitive to the new physics. And in this case, you have to some regime, which is a transfer momentum Higgs is comparable to the top mass. Okay. So near this threshold, the subleading terms would be become important. Okay. So this term has never been computed at two-loop QCD order. So that's a quantity we are going to present. So look at the next leading order, the dimension 7 operators. We would have an edge coupled to trace F cubed, 3 F terms, or 2D plus 2 F terms. Okay. So you find that the basis that is enough to have 4 operators, which provide a unique basis. So we want to compute this one, the Higgs to 3 parts vector, including 2 parts. So just for terminologies, the Higgs amplitude actually can be understood as the so-called form factors, which is a matrix element between three unshelled states times the operator. The operator is the same as before, just a strip of a Higgs field. So there's operator relations, which is just the detail is not important here. So as another maybe technical part is let me just briefly explain how we compute these two loop amplitudes. So the idea we use is unshelled entirety methods, which is together with the integration by parts, but in a not traditional way. So for some of you maybe not familiar about unitarity, it's basically to reconstruct your very completely high loop quantity by lower loop, or sometimes even tree building blocks. Okay. So looking at this just a one loop computation. Okay. So we know that final answer can be written as a triangle integral and a bubble integral times the coefficients. Okay. So what you want to know, physical information, is actually what these coefficients are. Right? So unitarity tells you that you don't need to look at the full one loop results. You can do in CAS. So it factorizes, under this CAS, it factorizes into a very simple 2-point tree times a very simple 4-point tree amplitudes. Okay. So your building block is just this very simple amplitude, and you can reconstruct these two coefficients. So the detail, lots of detail may be behind, but it's still, this calculation is just a half a page calculation using hand. I can explain, write every detail in 10 minutes, no problem. But here, just have an impression here. It's reduce the problem significantly. And the integration by parts basically is now a very standard tool to do a high loop computation. It's what I said to do integral reduction. Basically, it's just based on this total derivative of the integral is 0. Then you get a set of linear relations between different integrals. And this allows to reduce a small set of master integrals. The details is not also not important here, just how complicated it is, I mentioned. So let me just say that the traditional strategy is to first apply the empirical CAS, then you make a reconstruction to the full integrand. Okay. Then after get the integrand, you do RVP. Then you have a master expansion. The alternative strategy that we use is just starting from the CAS, do not reconstruct the full integrand, but directly do the IVP together. We do the IVP at the CAS level. Okay. Then for each card, you do this IVP. Then you collect all the cards, you find the full master expansion. So what's the advantage of this? So first, there's no need to reconstruct the full integrand. That would be a non-trivial step. Okay. And also, because your IVP is for a card channel, you can drop many other master integral which doesn't contribute into these cards. And also, because your input is a tree building blocks, your input is also very simple. So IVP is much simplified. And you also have different cards, so they have a internal self-consistent check between each other. So this is, I'm sorry I have no time for the many technical details, but this is actually not so important for the main theme, the hidden structure we're going to talk about later. So this is a strategy that we use. And in this particular problem, all cards that we need is just these 8 cards for this two-loop computation. And after these cards, we know the master coefficients, and all master integrals are listed here. They are actually known in terms of two-dimensional harmonic polylogarithms. So now, after this stage, we have the master coefficients, we have the master integrals, then we have the full bare form factor in terms of the 2D harmonic polylogarithms. So this step, we have the full bare results. It's still very complicated. You don't see the hidden structures yet. But you have the answer. So, so how about the structures? So it's a form factor of Higgs plus 3 gluon amplitudes. First, it has unshelled states, so it has IR divergence. Okay. It has 3 gluons, or 2 matrix quarks plus 1 gluons. And it has UV divergence because we are really considered QCD. First, the coupling requires normalization, beta function enters. And these operators they also requires normalization. It's like the Wilson coefficients. It's running by the change of the energy scale. So in down rec, this IR and UV are normally mixed in a non-trivial way. However, it's a very important fact people has known by lots of works by studying infrared divergence. The general structure is actually well understood. This is given by infrared divergence plus UV plus a finite remainder. And this IR part is universal. Okay. So that's very important. Universal, in a sense, is independent of operators. It only depends on your external patterns. It's a long-range interaction, so it's take a universal form. For example, in the exposed polynomials, the universal IR is only depends on two numbers, which is CAS polynomial dimension and collineal polynomial dimension. Actually, by integrability, in this case, we can compute non-perturbative this number. And after remove this universal IR, we are left is all of them must be UV, right? So this has to be absorbed by renormalization. There's a renormalization constant. And for X4, it's very simple, but similar, which is of course more complicated. Structure is also known for QCD. Okay. The details are given here.
What is the polynomial
Sudakov form factor. Yes, that's very important too. You can use Sudakov form factor. The Sudakov form factor also takes this structure. Yes, it's just it's a two-point case. So as Ij can only be 1 and 2. The only is that you have more than two particles.
And how do you see the double logarithm?
Double logarithm. Okay.
Epsilon square.
Right. This is a very interesting, very nice question. This is actually. For my understanding is that you can use this icon limit, so this Sudakov factor becomes a Wilson loop, right? Then if you compute the log of the Wilson loop, you can choose a particular the axial gauge, and in this gauge you can see all the Feynman diagrams when you take the log, they only have a double pose. So this is in a spatial gauge. Spatial gauge this can be manifest. That we can talk about. And okay, and as we already said, in the dimension 6, you have this more than 1 operators. So they have the same dimension, same quantum numbers. So of course they can, you cannot exclude possibility they can mix it with each other. So this is the basis that we choose for 1, 2, 3, 4. And we find at 1 loop there is no mixing, but starting at 2 loop, this renormalization matrix constant is start to mix with each other. So you have a non-trivial, non-diagonal matrix. This is the complete QCD results. Actually, we can the strategy, the computation strategy is very efficient. We can even do up to dimension 16. So we have this already have this result. So this divergent part is well understood. So what's genuine new information is actually into the finite remainder, which we really want to do experiment, right, to compute cross sections. So so the hidden structure that we are going to focus is about this part. So first, review the case. So in the 3-pattern case, you only need to care about 3 configurations. 2 of them are gluons with different helicities, and the other involve 2 parts. That's the only possible configuration, plus the conjugation. And if you only focus on gluon states, there is no non-planar configurations. You only have the leading term. And so this is, if you consider this trace add cube term to 3 gluons, then this is degree 3 parts. And this is basically what I mentioned last year. We find that the maximum channel are identical between X1 and X. And how about this contain fundamental parts? Okay, they're not adjoint particles. So in this case, they have n² terms, nc to the 0, and even 1 over nc squared. So this is strongly non-planar corrections. Okay. So it turns out this structure is not very nice. You should expand that in terms of quadratic Casamiers. One is the CA, the other is CF, fundamental So you see the right. This is not actually. If you take a larger limit, the CF will become actually half of a C. So in this expansion, we present this result. You have three terms. The maximum transcendent part, I should mention, this NF term has no maximum transcendent part, which is a variable number. So you have these three terms. Each of them is very complicated, and each of them contains also multi-poly logarithm. There's no way to remove them. Okay. We cannot simplify them into the classical poly logarithm. However, if you sum the three terms together, okay, this is a contained quark, okay, quark and gluon. But some of them three together, they become identical to the to the maximum transcendent part of the three gluon case, which is remarkably simple. And this we are considering this trace F square operator. But similar, if you consider this trace F DDF, which is actually equivalent by equation motion F side after side, you also have three terms, which is involve the multi-poly logarithm, which cannot cancel. But the same, add them three together, you also get equivalent to the another trace F cube, Higgs amplitudes. Okay. So the similar structure seems to be a universal pattern, which are much simpler. So what's the meaning of sum them three terms together? Okay, they have different colors, which is CA square, CACF, CF square. So this the physical interpretation is actually very simple. Just identify this fundamental quadratic Casimir as a joint quadratic Casimir. You see the CF identical to CA. It's not a large limit at all. Okay, it's really you need a finite n to make this map, and this will be equivalent to the maximum transcendent case to three gluons, also to that of X4 form factor. So this actually, for the form factor, you can even consider other operators does not necessarily belong to the Higgs effect action. It's more general operators. It's still a lot of example we show is still true. Okay. So this is the detail is not so important here. It's just a classify of joint operators or involve two fundamental fields. So this is how about the lower transcendent parts? So this is we found that the degree 3 terms, they're actually given by this T3 function, which is a non-trivial, involve non-trivial Lie 3 functions. And for the D2 part, you have this building block T2 here, which is also D2. And just flash the results. For this lower transcendent parts, we found that this involve quark in states. For degree 3 parts, this is not maximum transcendent parts. All of the Lie 3 terms are contained in this T3 function. What's left is only pi squared times the log, or it's a zeta 3. So if you just naively do a bare form factor, it's a very huge expression. So for us, we actually obtain this result by test and guess. The guess is T3 can be a universal building block. It turns out that everything can be retained in T3. Okay, so this is also not obvious at all from the Feynman diagrams up to these very simple terms. So in the last couple of minutes, let me just explain what's correspondence. It's some work in progress. And the idea is to apply physical constraints. As we said, the huge intermediate expression, but the final results are much simpler. Okay. So for example, the universal IR divergence, this can be used to fix a finite part. This may be not obvious at all. You only know the divergent part, how to use the fixed finite part. The idea is to expand your results in terms of this uniform transcendental integral basis. Okay. So your full answer is written as this integral are uniform transcendental. They times the coefficients. And this coefficients is expansion in terms of the epsilon parameter. Okay. I said this different power of epsilon will have different transcendental degrees. So you know the QCD answer have different degrees, but all these different degrees are not from this basis integral because it's uniform transcendental. It's only come from the different power. So if you want to consider only the maximum transcendental terms, you take the epsilon power to be the lowest, because epsilon have transcendental degree -1, right? So it's the lowest the epsilon to the 0 terms, it has a maximum Chernov degree. For 2 loop, it's a degree 4. So now you just compare this integral by required to match with the universal I divergence. Actually, you find that the finite part also fixed. It means that using the I divergence is enough to fix the coefficients. But this integral not only contains divergence, but also the finite parts. This may be a little twisting, but the physical information is this coefficients, and once you fix these coefficients, you know this answer to all of them. So that's so let me just emphasize that for the minimum 2-loop form factor, basically the results I announced last year, we can now just bootstrap it without any computation. It's fixed by the infrared divergence for the maximum Chernov parts. So similarly, for the lower Chernov parts, you can also partially fix it. It's not fixable by IR, but it needs some extra very simple CAS. So let me just summarize the hierarchy of the complexity here. So if you look at the function, okay, algebraically, the higher degree the function is, the mathematically is more complicated, right? And if you look at it physically, it turns out that the higher degree, they are simpler to fix. The most non-trivial part is actually the rational parts, which are mathematically very simple. Okay, so this is the lesson that you by disentangle results into different channelity degrees. So just to summarize here. So we have found that Higgs amplitudes with higher dimension operators always external quarks. They also satisfy this principle. And for this case, it can be proved using physical constraints. And for the lower Chernov parts, the simple structure also exists, and it may be fixed in a simpler way. So the new strategy is that you can divide and conquer with a different Chernov degree, and then using physical constraints, bootstrap results without intermediate computing steps. So hopefully this will towards a better way of computing and realistic conceiving. Sorry about it. Thank you.
Okay, thank you. So but we are running out of time. So bunch of question or comment is acceptable.
So in your case, that's for the highest transcend, I don't know how to pronounce it. Okay. So you just give us you can fix it by using the UV divergence. So that's independent of which theory is?
Right, yes.
So it doesn't matter it's QCD or into form.
This structure, this method is independent of the theory.
Okay.
This basically is just a mathematical structure.
Mathematical structure.
It's not different theory use different constraints.
Sorry, so is it like QCD in the spaces here the same coefficients?
For the maximum Chernov part, that if you it turns out that the coefficient is the same. That's explain why the maximum Chernov is universal. But the story here is that you can use the same technique to go beyond maximum Chernov parts. It provides a computational idea to do that.
We don't have any physical reason behind?
Physical reason.
Yeah.
The physical reason we use is this universality of some divergence. Yeah. Also, you can plus this many other constraints like collinear limits or simple binary cards. They also can enter as constraints.
Okay, so then
Thank you very
the
much.
speaker, okay?